Good afternoon, everyone, and welcome to today's Innocen webinar. It's actually a great pleasure to see such a global audience joining us today to explore how to convert challenging chemistries into scalable and safe solutions. My name is Ivona Kaluzna, and I will be moderating today's webinar. A few practical tips before we start the webinar. The webinar is being recorded, and therefore you will be able to request the full recording at any time. If you came late or you cannot join at all, you will be able to watch it afterwards. The Q&A and chat room is open for the entire session, and you can place any of your questions during the presentations. We will address any of your questions at the end of the webinar during the Q&A session. And to set the scenes for today's talk, I would like to say a few words why this particular subject is relevant for us and probably for many of you joining the webinar today. As you might know, reducing reagents such as DBAL are one of the most powerful and selective tools in organic synthesis. At the same time, this reagent is highly exothermic and very reactive, which makes it very difficult to apply that reagents for chemistry at scale. And these type of reactions are perfect examples to show how we can push the limits of traditional batch processing by using flow chemistry and enabling better control, higher control, safety, and confidence at scale. And with this word said, I think it's a perfect time to introduce, it's my pleasure also to introduce our speakers of today's webinar, Raf Reintjes. Raf Reintjes is our principal scientist in Flow Group at Innocen. He brings extensive experience across process development, pilot plant production, and implementation of chemical processes in different chemical sectors. Actually, Raf combines 40 years of experience pushing the boundaries of process development and transforming chemistry such as DBAL into a safe and scalable continuous solutions in the industry. And having said that, I think this is a perfect time to start officially our webinar. Raf, the floor is yours.
Thanks, Ivona. Thank you for your kind introduction. I will start with sharing my slides. Today's subject is the exothermic DIBAL reduction of esters to aldehydes, which Ivona already pointed out. But before we start talking about that, I would like to introduce Innocen as a company for you, for attendees who are not so familiar with us. So Innocen is an independent service provider of process R&D and custom manufacturing. We are located in the south of the Netherlands at the Brightland site in Geleen. Currently, we have a team of about 70 people available to work for you. Although we are a young company, founded in 2017, we have also people with large experience basis, because in the past we originated from an DSM R&D organization. And during that time, we built up a significant track record in successful implementation and optimizations of all kinds of processes up to implementation in a real production environment. So with all these expert people and on board, we are able to give you a full solution provider. Our expertise base starts with finding out which chemical pathways would be the most beneficial for your chemistry. We have all the expertises available to then do process development in the lab, design and develop and manufacture our own flow reactors, including the kinetic modeling and calculations that need to be done. And finally, of course, we are able to scale these reactors to pilot scale and to production scale and help you implement it in your systems. Now, coming to the subject, ester reduction with Dibal. Typically, you see these kind of fine chemical conversions being done in fine chemical industry in a batch reactor. Now, the batch reactor is a very versatile type of equipment, but it also has a list of limitations, very familiar limitations, which you all know, of course. But I want to highlight the most important one, and that will be the limited cooling capacity. And that makes it extremely difficult to maintain temperature control during this reduction. And typically in a batch mode, this is done by slower dosing of your reagent, the Dibal H. So not the intrinsic kinetics produce the productivity of your system, but the dosing rate is telling you how fast you can produce. And this has to be slower than the cooling capacity of your reactor. Now, how can we better tackle that problem and gain high productivity? Best thing so far is to switch from batch mode to a continuous mode. And there we have, of course, different reactor systems at hand. The most simple one would be a continuous stirred tank reactor. But in that case, we lose control over the time component. CSTRs have a very broad residence time distribution. And also this is not what you would like. So moving down and then gaining more control over time, we end up with tubular reactors as the ideal reactors for such a fast exothermic reaction. Let's see. Now, tubular reactors, and especially tubular flow reactors as we have designed, they pose very advanced capabilities, which enable us to do these instant chemistries. And that comes from the fact that these tubular flow reactors with millimeter-sized channels provide us with enormous heating and cooling capacity and instant mixing. And that enables us to handle chemistries that produce unstable intermediates. Next to that, these small-sized channels, we are talking 1 to 4 millimeter channel sizes with just 0.5 millimeter of wall thickness. Nevertheless, the wall is very thin. They are extremely pressure resistant, which means that also high pressure reactions, high pressure process conditions can be handled. So, for instance, low boiling solvents can be handled at very high temperatures, way above the atmospheric boiling point of your solvent. And finally, the increased heating and cooling capacity gives you process control over the main parameters that are important. These channels will be fully filled, so there is no headspace available, and the high productivity will translate in a low processing volume, which is in hazardous chemistry, of course, essential when you are handling dangerous goods. Here you have a number of examples of 3D printed flow reactors, small ones for the lab and larger ones for piloting. As Innocen, we opted for a modular design concept, modular in the sense that we will have different functionalities and different volumes and sizes, so that we can apply these modules and reconfigure them easily in the required reactor setups that we need in our lab and in our piloting investigations. And of course, later when such a reactor system needs to be scaled to your plant situation, then you get a dedicated designed and manufactured reactor. Now, to be able to create all these excellent capabilities, we need to vary the configuration, the geometry of the channel, the size of the channel, so diameter and length, and shape of the channel. And for that, it was advantageous to use 3D metal printing as a new manufacturing technology, because 3D metal printing allows us to apply that design freedom that we require for that high performance. Now, 3D metal printing is a new manufacturing technology. It's around for the last, say, decade. It is accompanying typically with a low material consumption. As I said, channels are in a few millimeters diameter and have only 0.5 millimeter of wall thickness required to withstand pressure. And you are not, you have used an additive manufacturing technology, meaning that you put construction material only there where you need it, whereas many other construction manufacturing technologies are destructive. They take away material from a large chunk of material. That makes it more expensive in the sense of construction material cost. Now, which metals can be used in 3D metal printing? Any metal that can be welded is suitable for 3D printing. Typically, we use stainless steel as the working horse. Many reactors in chemical industry are stainless steel, but for corrosive systems, we can switch to the Hastelloy, the high nickel content alloys, Inconel, zirconium, or even tantalum. Now, on the right, you see an example of the scope that we can achieve. So processing conditions in these modules can be from -100 to +300, and from, say, a vacuum to above 200 bars. Mixing times can be as short as a millisecond. The heat transfer coefficient can be between 1,000 and 8,000 watts per square meter Kelvin. Heat transfer area 1,000 to 4,000 square meters per cubic meter. And this allows us to get highly productive modules with capacities up to a few thousand tons a year in just 1 liter of a volume. Now, where does this high volumetric heat transfer capability come from? Now, the volumetric heat transfer capability is calculated from the overall heat transfer coefficient in watts per square meter Kelvin per square meter Kelvin, and then of course multiplied by the volumetric area, heat transfer area in square meters per cubic meter of reactor volume. Now, we investigated these factors, these parameters, and we started with, of course, the heat transfer coefficient to get that a little bit higher, to improve it from the batch situation. And therefore, we designed temperature and heat transfer flow cells to measure it. So in the bottom part, and you see my mouse on. So in the bottom part here, you see such a typical flow cell, heat transfer flow cell. Here we have heat transfer fluid was flowing through the main tube, and we have a part of reactor channel, in this case a zigzag channel of 1.13 millimeters diameter. We have the possibility to flow with a certain processing fluid through that zigzag channel, while we can insert temperature probes at the beginning and at the end of this section. So we can measure heat transfer coefficients over a short section, and then vary the turbulence at the processing site, while we also are able to vary the turbulence at the heat transfer site. And the wall thickness is, of course, in all these measurements the same. But since that is only 0.5 millimeter of metal, and the high conductivity of metal then results in a situation where this wall is not posing any resistance to heat transfer. Now, I want to please give your attention to this graph here. On the vertical axis, we have the heat transfer coefficient on the processing side. measured. And here we have the turbulence, the Reynolds of that processing side. Now, as a function of the turbulence at the heat transfer fluid side, we see these typical curves. And what we are able to do is it starts at about Reynolds 200, because there we see this positive effect deviating, and the flow characteristics are deviating from laminar flow. And we start initiating already secondary flows, the onset of the real turbulent flow, which we would expect after Reynolds 4000. And what we achieve is that the Nusselt number is increasing significantly, therefore giving us a better heat transfer coefficient, starting at about 1000, and even the ability to go up to about 8000. Typical values, when we want to avoid high pressure drop, typical values are more or less around 2000 to 4000, which means that Reynolds numbers should be between 1000 and 2000. Now, that is a significant improvement compared to batch. I would say at least a factor of 5 compared to a batch reactor. But then the most important increase in heat transfer capability is stemming from the fact that we use these small diameter channels. A small diameter channel, directly following from its size, gives us 1000 to 4000 square meters of heat transfer area per unit of volume per cubic meter. And when we put all these numbers then in a table, we see that a typical batch reactor, which is doing well, will have about a heat transfer coefficient of 500, an area of about 4 square meters per cubic meter. This holds for, say, a reactor with 1 meter diameter, and gives us a 2 kilowatts per cubic meter per degree Kelvin heat transfer capability. Now, for this zigzag flow system, we saw an increase of the heat transfer coefficient towards 2000, say a moderate increase, and then a very large increase just coming from the small diameter of the channel. And this all adds up to at least a factor 1000, sometimes a factor 2000 increase in heat transfer capability. So you can imagine that whenever you are conducting fast and exothermic kinetics, such a channel will be a real improvement towards heat transfer capabilities. Having a high heat transfer is one thing, but how to be sure and how to monitor that. And here comes a second feature stemming from the design freedom of our 3D metal printing. We are able, although the channels have only a few millimeters in diameter, we are able to design our modules in such a way that we can insert small diameter temperature probes. You can see that here, that blue line here is a small diameter temperature probe that can be something between 1.5 and 0.5 millimeter, inserting directly into that channel. And we can have multiple of these inlets for probes in a lab scale reactor. Here you see the diagram, the scheme of that reactor. There's a process inlet and a process outlet, and while the fluids are flowing through or reacting, we can measure the actual temperature profile. And these larger inlets are there to allow the heat transfer fluid to flow through, and to achieve high Reynolds number, we have to have more space. So these channels are much wider than the reaction channel and have higher flow rates. Then providing these high heat transfer capabilities is something that we tailor at lab scale. So the reactor design used for your chemistry is tailored to the needs of your chemistry, meaning that the channel performance is optimized in the lab. Geometry, size, volume, residence time, all these aspects need to be optimized in the lab together with the processing conditions. And then to allow to have a robust scale-up, we rather keep these parameters size and geometry the same, or at least close to that value, so that the actual increase of production capacity, production capacity, I must say, is coming from the fact that we pack multiple of these channels in parallel in a single reactor module. And if that doesn't allow or doesn't provide the required production capacity, we can have multiple of these modules again in parallel, but then externally to gain in capacity to your desired target capacity. So we are able to manufacture real plant scale flow reactors, but there is a second aspect to reckon with. When plant scale commercial flow reactors are to be used in a plant, they have to comply with legislation. So, and the first thing that you then encounter is that we have to comply with the Pressure Equipment Directive put forward by the EU. And this tells us that when the volume of the reactor set up, the design pressure, the design temperature is above a certain value, you need to certify that your reactor is safe to be used. This is a procedure which is well known for batch and large scale reactors, but for 3D metal printing as a new manufacturing technology and flow reactor as a new reactor system, this was not previously known or done or demonstrated. And I can tell here that we have done recently some customer projects where we provided commercial flow reactors, and together with a notifying body and our 3D metal printing service provider, we went through the whole procedure to require that certification. And this typically means that you have to show and demonstrate to the notified body that your printing parameters are qualified to do so. The build space in which you are printing has to provide in every position the provide the right properties of the metal, meaning that yield strength, tensile strength, elongation, that kind of material properties have to be met in every printing direction. You can imagine if you print in the vertical axis or in one of the horizontal axis, there might be slight differences, which you have to then show that you don't have them. And furthermore, the printing service provider, the company itself, has to show that their quality management system is of a certain level. Quality assurance of that production process has to be there. The product itself has to be looked at, meaning that you have to have a qualified design. And finally, we have to show that in a hydrostatic pressure test, we can meet all the requirements. Now, Innocen proudly can announce that we have done this and we are able to provide it to you whenever you would require a commercial flow reactor from us. Now, sorry for this a little bit long introduction. We can now move on to our actual case study, the reduction of an ester to an aldehyde with the Dibal-H. This reduction of ester is typically done in a two-step approach to avoid selectivity issues, meaning that you reduce the ester first to the alcohol and then oxidize again to the aldehyde. Now that is a laborious route, and therefore people or industry rather uses Dibal as a reagent, because Dibal allows you to partially reduce the ester to exactly the aldehyde that you need. The only downside of this is that this reduction is strongly exothermic. It's about minus 200 to minus 250 kilojoules per mole. And the it goes through a tetrahedral intermediate, which is only stable at very low temperatures, say -70 degrees Celsius. When the conversion of the ester to the intermediate is completed, then you can quench the whole system with protons coming from either methanol or an aqueous acidic quench, and then the aldehyde is released. But during that whole process of Dibal dosing, there is need for this cryogenic temperature to keep the tetrahedral intermediate stable. Now, why is that so important? Here again, you see the mechanism depicted. The ester forms together with the Dibal a tetrahedral intermediate, which is unstable. And it is very important that this intermediate doesn't degrade and release aldehyde prematurely. Of course, while you are conducting this Dibal dosing and this conversion to the intermediate, any formed aldehyde would immediately yield loss of selectivity due to overreduction and alcohol formation. Here you see that depicted in this second part of the mechanism. The aldehyde, just like the ester, would also form an intermediate which after quench would be transformed to alcohol. So it's very important that we keep that tetrahedral intermediate at the beginning very stable. Now, this then poses problems when using batch reactors for this conversion. Batch reactors have a limited cooling capacity. In the lab, there is still quite some area to volume present. But when we scale it up from, say, a 100 milliliter reactor to a 100 liter reactor, this area to volume ratio declines strongly. It depends on the size of the reactor. This area to volume ratio decline will lead to even further decline of cooling capacity, and means that the dosing of the Dibal has to be even slower than it was in the lab to maintain the cryogenic conditions. And during all the dosing time, your tetrahedral intermediate needs to be kept stable. Now, that reduces the Dibal dosing flow. To maintain temperature control, and low dosing flow immediately translates into long exposure of that unstable.
We apologize. We had a small technical issue. We lost our connection. So we're back on track, and Raf will continue.
Okay. So here's a few examples, lab scale examples of batch reductions with Dibal. And you can see that we have to keep here, or they kept temperatures at -78 degrees Celsius and had dosing times of half an hour to 1 hour to get all the reaction heat out while maintaining that temperature. Now, selectivities are not that great to lose a lot of yield towards alcohol formation. And the way to improve that, of course, as we pointed out earlier, is to switch to continuous mode. And here is an example of lab scale Dibal reduction in a flow reactor, in a small flow reactor. And you can immediately see that the 1 hour reaction time, dosing time that the batch reactor had is reduced to even less than 1 second here in this example from MIT in 2012. The yield is 96%. There was almost no alcohol formation, but that stems from the fact that also the conversion was not complete. So we had here the example had about 96% conversion. Now, let's move on to our lab scale investigations. Here we have the procedure that we followed. The Dibal reduction and the methanol quench are, of course, executed in a cryogenic environment at low temperature, then followed by an aqueous quench with acid. a liquid-liquid extraction to separate the product and catch it in the organic phase. And finally, full analysis of both organic phase and the aqueous phase. The reactor that we used is depicted here on the slide. It's the RL100 reactor with the 4 temperature probes in. Let me put this at a different position. It's a 3.94 milliliter reactor with a 2.2 millimeter channel diameter, and it has a surface heat transfer surface area of about 83 square centimeters. After this production of the tetrahedral intermediate follows the methanol quench, and on lab scale we used a static mixer for that with a small diameter, again only 3 millimeters. Pilot scale used a little bit bigger one of 8 millimeters, and 3D metal printing comes to help to aid here, because the internal structures of such a mixer have to be very intricate, and that is only possible with 3D metal printing in a 3 millimeter channel. Here we have the full setup that we used in the lab as a process flow diagram. Of course, it looks very complicated. I will try to explain a bit more what we see here. First of all, there are a number of gear pumps required for all the reagent flows that we need. Gear pumps are chosen because they have very pulsation-free flow. And of course, to measure that, we applied mass flow controllers. These mass flow controllers directly set the pressure, the flow rates for these gear pumps. So there is a process control system, flow control system for every reagent flow that is required. Then there is extensive use of cryostats. We had to use 3 cryostats in the lab because there was a large amount of heat to be removed. First of all, the pre-cooling of the reagent flows to a very low temperature. Then, of course, in the reactive system, we have the reactive heat that needs to be removed. Now, we used in our experimentation 25 mass% diebal in toluene, which we then could dilute further to the required concentrations by adding dry toluene at this mixing point, after which the desired concentration would flow towards the reactor. On the bottom side, you have the dosing system for the ester and the methanol for the methanol quench. Again, the pumps and the flow control systems, and the mixing of the ester and the diebal happens at the reactor site. Methanol is then added at the static mixer just subsequently after the reactor. Okay. What were our results? We were able to vary residence times in the range of 1.2 to 1.9 seconds. The diebal equivalence in the range of 1.1 to 1.4. You need a small excess of diebal, but of course you don't want to have a too large excess, otherwise you risk over-reduction in the methanol quench. Temperatures were varied from -40 to -55 degrees Celsius, a little bit higher than we saw in the examples of the lab publications. And with that, we achieved partial reduction of that ethyl hydrocinamate substance that we put in substrate. Okay. Production capacity ranged from 0.16 to 0.22 kilos per hour, which is already quite significant if you imagine that the reactor has only 4 milliliters of volume. Now here are the results: temperature, residence time, diebal equivalence, and then what we saw is that we saw nowhere during this experimentation clogging, which could be achieved when you are not when you have some moisture in the system and the dye bulb produces alumina salts. So that dry operation was secured and provided us with no clogging. Then where is it? Conversion was very high in the range of 98 to 99%. So only a very small amount of ester was left after the dye bulb addition. Then when we look at the selectivity that we could achieve, the alcohol formation that we have witnessed, we saw that the temperature of the reactor is a key parameter. At the very low temperatures of -52 degrees, we achieved little alcohol yield, and the higher the temperature was, the more of this alcohol over-reduction was visible. And of course, that directly is related to the stability of that intermediate. Best results were then achieved at the lowest temperature, -52, and a significant yield of, say, on average 97%, with just 1% of alcohol over-reduction was our final result. Now, when we look to the data that we measured, we see here the temperature profiles that we determined while we were running this synthesis. You have to imagine the reactor is at a steady state, so at the various positions of these temperature probes, you will find steady measurement of temperature. The inlet temperature is depicted on the vertical axis, -52, here it is 47, and here it is 38. So there is, what can we see here? There is a close to adiabatic temperature rise directly after mixing. And this relates to the very fast kinetics of the diol H reduction. The total residence time over the full reactor volume is 1.1 to 1.9 seconds, but you can directly see that already in the first 0.1 second, the full conversion is achieved. And while the reaction mixture is then proceeding through the reactor, we are merely cooling down the reaction mixture back to the temperature at which we entered. And then stability of the intermediate, of course, decreases at higher temperature range. The greenish and the orange line, they have on average a higher temperature, and therefore the intermediate is exposed for longer times to high temperatures, and thereby you have degradation and loss of selectivity. And pilot plant investigations were conducted a few months later. We again followed the same protocol, reaction and quench in a cryogenic environment, aqueous quench, and liquid-liquid extraction with full analysis of organic phase and aqueous phase. For the cryogenic environment, for the reactive part, we used our multifunctional skid, which is depicted in this picture. It's equipped with gear pumps, but then of larger capacity. There is a box, cold box we call it, around the individual heat exchangers and reactors. I will show that in the next slide. The box itself is flushed with dry nitrogen to avoid any condensation of moisture or ice on your reactor module, so that you still are able to quickly change to other modules if necessary. The samples that we produced are, of course, far bigger than we did on lab scale. Here we have about 1 liter bottles of sample. The pilot setup, the process flow diagram, looks quite similar to what we had in the lab, but is of course of a much larger size. In this case, we applied stainless steel reactor and heat exchanger modules, but there is no corrosion issue, but these modules were better available at that moment, and the heat conductivity of stainless steel and Hastelloy are practically identical. They deviate a little, but the heat conductivity of the wall doesn't pose any limitation to the heat transfer capability. Volumes are bigger. Here we have about 17 milliliters, but interesting to show that we kept the internal diameter and the shape, the geometry of the channel the same to secure a robust scale-up. Now, again, cold box, this is the environment where all the cryogenics happen. Reagents are provided from outside, pumped pulsation-free in flow control mode into a mixing section where the dry toluene is used to set the desired dye-ball concentration. The 0.3 molar ester is pumped in. Dry toluene is used to rinse these lines whenever it is needed after the experiment. I think it's worthwhile to highlight that the fact that we had no clogging during our experimentation is caused by the fact that we used very dry toluene and solvents, less than 30 ppm of water. And finally, also dry methanol is used in the quench. The pilot plant is equipped with one large capacity cryostat, so we don't have to hamper with three separate cryostats to get all the reaction heat out. And here you see a picture of the setup in full action. The heat exchangers for dye-ball here in the bottom, ester just above it, and the methanol quench here are located inside this cold box. And then here, this small box here is the actual RP100 reactor module with 17 milliliters of processing volume, where the dye-ball H is directly reducing the ester to the aldehyde, or to the tetrahedral intermediate. And then this intermediate is the reaction mixture with the intermediate is flowing out and on the top and is transferred to this static mixer up here. There is another reactor module visible, but that was not used in this experiment. Here you see the flow skid in our experimentation room, and the cold box closed and flushed with dry nitrogen. And the process control and data logging is done from this control cabinet standing next to it. Again, we applied similar ranges of variations in residence time, dye-ball equivalence, and temperature. We achieved a way higher production capacity, and these are our results. Again, there was no clogging observed. High conversions achieved, about 98% of conversion, a little lower than what we had on the lab, but we could duplicate the side product formation, the alcohol over-reduction formation quite nicely. As you can see, at lower temperatures, we had less than 1%, the 0.8% of alcohol, and the higher the reaction temperature goes, the more alcohol is produced. Again, directly translated and correlated to the stability of that tetrahedral intermediate. The best result that we could achieve was at the lowest temperature of -55. And the yield in alcohol, 97%, the yield in aldehyde, 97%, and alcohol fits nicely with the lab results. Again, also in the pilot reactor, we have these temperature probes. In this example, we had a reactor with only 3 temperature probe inserts, but the picture really resembles what we had in the lab. A fast exotherm and adiabatic temperature jump in the beginning, and then a similar cooling curve as in the lab. This is shown in this graph where we took out a lab scale example of -48 degrees Celsius with a piloting example of -50, the orange dots. And you can see that the jump is quite similar. And then the temperature profile follows this gray trajectory, ending up at full cooling at the end of the reactor. This temperature jump in the beginning, high temperature, adiabatic temperature jump in the beginning, is actually they're posing a problem. It exposes our tetrahedral intermediate to a much higher temperature, and that causes this 0.8% of alcohol over reduction. And we think that a single injection point, as we applied it here, is hampering us. We expect that multiple Dibal injections, so multiple dosing points, would be an improvement. Because after every dosing point, it's possible to cool back to the original temperature. And by spreading the release of the total reaction heat over multiple points, we guess that we can achieve, on average, a lower temperature and therefore a better result in the alcohol over reduction. Now, then finally, I would like to show you this, or summarize the best results that we could achieve in the lab and in pilot. I think the table speaks for itself, and it is a nice representation of a successful scale-up of this very challenging chemistry. Dibal reductions of ester can have high yields and low over-reduction, combined with high productivity, 40,000 to 70,000 kilos per cubic meter hour. Temperature is the most important factor to be controlled to avoid over-reductions. 3D printed flow reactors provide excellent heat transfer capability, as you have seen, and the reactor performance was successfully scaled from lab to pilot. Now, with that, I would like to conclude my presentation and allow you to thank you for the attention and allow you to give us some questions. So,
thank you, Raf. And let us move to the Q&A session. Sorry, I have to put my glasses on to read it. What we have. All right. So we hope you guys found that presentation valuable and informative, and we show you clearly how we scaled up challenging exothermic reaction from the lab to the pilot plant scale. So I see that we have a lot of questions in our Q&A part. So let's start with answering one by one, and the one which we won't be able to answer in this session, we will follow up via email. So let's start with the first one. Raf, are you ready for the challenge?
Go ahead.
So the first question. Inocen claims to have superior heat transfer, but still observe a significant raise of temperature after mixing the components. Are there options to prevent this, besides the mentioning multi-injections?
Of course, there are more options. Yes, there is although we have this flow reactor with excellent heat transfer capability, we still end up in a hotspot at the beginning of the reactor channel, which is hampering us. Next to multiple injection of Dibal, I would propose an option to go down with the concentration of the ester and Dibal. We used a small excess of Dibal to reach full conversion, but since we were aiming for a high productivity, we operated the lab and the pilot with 0.3 molar ester. Of course, if you reduce that concentration, there will be much more solvent toluene available to take up the heat, and the adiabatic temperature jump would be far less. But the downside for that would be that you cannot reach the high productivity because you dilute the system. So you will produce less kilos per cubic meter per hour. And after the synthesis, there will be a larger mass of solvent that needs to be recovered and handled in downstream processing. So reducing concentration is a valid one, but there is a price to be paid.
Okay, all right. Thank you, Raf. The next one. When comparing the literature of 2012, the MIT flow paper, with our results, so that we obtained, it becomes clear that you guys have a higher fraction of aldehyde, 96% to 98%. How much alcohol is formed in the 2012 publication? Do we know that?
Yes, I mentioned that. The publication achieved an aldehyde yield of 96%, but with zero alcohol formation. But the reason for that was that they used a lower concentration, which of course gives them less hotspot formation. And they started with a lower temperature, -78. So they never reached that level, temperature level, where the tetrahedral intermediate is degrading. Mm-hmm. So when that's what we experience. We try to push productivity to a very high level, but then we are punished by a few percent of alcohol formation, which we then could minimize by working at -50 degrees Celsius. Okay. At -78, you will not experience so much degradation, but of course the cooling to that low temperature level is a high expense.
Yes. Yeah. All right. The next one, it's slightly different. What was the time needed to go from the lab to the pilot plant? How much time it took us to go?
Okay, that depends. Of course, it will take time to design your piloting reactors, to prepare the 3D printing company to print the piloting reactors. It depends on the complexity of say, the chemistry. And in normal, typical cases, I would say that there'll be something between 4 to 6 months. But don't pin me down, because it depends on how complex is the chemistry that the customer will bring us.
Yeah. It will always depend on the complexity and the time and how much we need to invest.
Yes, but still, I think that 4 to 6 months is still a very fast trajectory from having optimized your lab situation to running in a pilot plant at a way higher capacity.
Yeah. The next one, it's okay, also related to the MIT paper. Why did the MIT people achieve 0% alcohol and Innocent still has about 1%? Can we explain that?
Yes. Like I said in the previous answer before that, when you start at lower temperatures, -78, and you have a more dilute system, the temperature jump that you have, the kinetics will be as fast or close to, and the temperature jump will be less pronounced. Therefore, you will not enter the domain of -30, -40 degrees Celsius, where the residence time and the exposure over to that temperature will attack the tetrahedral intermediate and release prematurely the aldehyde. So if you do not touch that intermediate and you leave it intact, you will see very little over reduction. Mm-hmm. But again, price to be paid is deep cooling, dilution of your system, and therefore loss of productivity.
Loss of productivity.
How that translates into process economics, that has to be seen with every individual project. how bad is it if some alcohol formation over reduction occurs? Is it just a matter of loss of say, overall aldehyde yield? Then 1% additional alcohol may not be an issue. But if there is a separation problem in your downstream processing between the aldehyde and the alcohol, then it can be very beneficial to produce as little as possible of the alcohol.
Yeah. So looking at the time, we might take still one more question because we can spend one more minute. Our technical team is giving us a signal. So there's, by the way, there is still many questions that haven't been answered by us yet. But like I said, we will follow up on those. We will follow up with answers via email. The last one that we will tackle today: did you perform the initial lab results with the assistance of design of experiments, or was this done by one factor approach?
Good question. We applied in the lab experimentation the one factor approach. We kept multiple. So the design of experiments allows you to reduce the number of experiments that you do. But please bear in mind that the residence time at which we run such an experiment is 1 to 2 seconds. Meaning that you get a stationary state, a constant set of parameters after only a few seconds. So there's not much to be gained whenever you have set up your lab scale experimentation by doing design of experiments. We therefore chose to use a one factor system and look into every parameter which was important. And like pointed out, the temperature profile was the most important factor.
Okay. Due to the time, we have to wrap it up at that moment. Like I said, we will follow up with any unanswered questions via email. Thank you so much for your excellent questions and for joining our webinar today. If you have any additional questions that might arise after digesting the information that Raf just presented today, please feel free to reach out to us at any time. Thanks again and have a great day. Bye-bye. See you. Take care.